minus 1. 2 minus 2x squared. Drop your parentheses, distribute the negative through, collect like terms. 2 minus 2x squared. That's how wide this is. But since these are squares, that's also how tall it is, right? So this side's 2 minus 2x squared. Any questions? No? All right, so what's the volume of this little sliver, this little slice, this little piece of bread?
2 minus 2x squared times 2 minus 2x squared times dx.
Yes, it's 2 minus 2x squared times itself again, so I'm just going to square it, right, and then just dx. That would be the volume of that little piece. And now add them up, right? Add them all together, and when we do that, we're going to bring the integral in. Okay, so integral time. I just erased the piece I need, but I think y'all can figure it out. The total volume, right? The total volume of the whole thing should be the integral from where to where. We didn't get those points of intersection. We didn't figure out where these were, but I thought they were obvious. Were they obvious? 1? Negative 1 and 1? Okay, you just get that by setting these equal to each other. Or just like look at it and be like, okay, yeah, negative 1 and 1 work, whatever. Either way, you could get that, right? Negative 1 to 1. And then use this formula right here for each slice. So 2 minus 2x squared, that quantity squared, dx. And we're in business. All we'd have to do is square that out, collect like terms, integrate, plug in, and we're done. So dot, 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 right? You could figure out the rest of that. Questions? Is that pretty straightforward? All right, let's change the problem. Let's do, instead of squares, let's do circles. Let's do full circles. Okay? Now I have to be a little bit clear, more specific in this. Circles. The diameter is in the xy plane. In other words, I'm telling you right there that the diameter of that circle is always the part that's on the flat piece, on the ground. So that's where you determine how long or wide the circle is. All right, so I'm actually going to draw this all again. I think it'll be a little faster this time. Blue on top, red on the bottom, and then over here, and draw it again. Let's get a little more practice. Go a little faster though. Oh wow, I missed. Forgot what I was doing. Okay, this has got to go through at the same place. Over here it's got to go through at the same place. All right. Good enough. So I've got circles, right? So I've got this little slice in here. It's got a little thickness to it there. That's this slice in here. And now that's the diameter, right? The diameter of this circle is in the xy plane. So that's my diameter of my circle. So if I draw a circle with that diameter, I get something like this. And it's hard to see because that's all cluttered up there. So it's easier to come, I think, over here to draw your circle. You just draw a circle, give it some thickness like this. Good enough. Now what we know about this circle is that if you were to look at the actual distance across, right? That distance across is equivalent to this distance, which is equivalent to this distance, isn't it? Right, from here to here. So what is the diameter of this circle? The diameter of this circle is what? It's going to be the blue one minus the red one again, right? Which we already did that algebra, didn't we? This is 2 minus 2x squared. Agreed? That's the diameter. I don't need the parentheses. I'm not sure why I did that. Agreed? Huh? No, this is the whole thing. This is the whole thing. So that's the diameter. Now, what is the volume of this? That's a cylinder, isn't it? Pi r squared times height. Well, we know what the height is. The height's really kind of just the width of this, which is dx. So I just need pi r squared. Yeah, the radius is half of the diameter. So the radius of this circle is half of that. Just distribute a half through, so you just get 1 minus x squared. Agree? Questions? So the volume of this little piece is equal to pi times your radius squared dx times the height dx. Pi r squared times height. That will give me the volume of one little slice. I just need to add them all up now. So the volume of this solid with this particular cross section of circles will be the integral -1 to 1 again, and then it'll be pi, which I can pull out of the integral, right? Because it's a constant. And then 1 minus x squared dx. Okay. What if we did semicircles instead? Just half of this answer, right? You could just do this whole thing again and just put a half anywhere you want. You could just throw the half right in here, right? Because that's the volume of the full cylinder. You want half of that, so you just put a half. So there's not a big difference in the formulas from circles to semicircles.
Could you wait till the end?
Mm-hmm.
Could you wait till the end?
Yes, you could. All right, let's do one more. Let's do equilateral triangles. What is an equilateral triangle? All sides equal. So I'm going to see if I can do this one by just drawing the sliver. Is that all right? Can I just draw the slice? Everything else is the same. So we have the rectangle that was on the ground, like this, and I create an equilateral triangle from that, like this, roughly. We know that this side right here should be what? 2 minus 2x squared. We've done that already. In fact, all the sides are that, right? So what is the volume of this thing? The volume should be the width of it, right, which is dx, right? That's in there. Let me throw that on the end. But the other piece, that other piece that we're missing, is the area of the triangle. Because all you do to get the volume is you find the area of the triangle and you multiply it by how thick it is. So what is the area of that triangle? And that's not a simple problem. Is it what? Sine squared what? The side squared. Let me draw you that triangle. Just looking at it, straight on. If we were looking at it straight on, not considering the thickness at all. If this side's 2 minus 2x squared, this side's 2 minus 2x squared, this side's 2 minus 2x squared, can you tell me what the area of that is? Ooh. Do you remember ever in pre-cal finding the area of a circle if you had all three sides? Law of cosines, the problem with law of cosines is that within the law of cosines there's an angle in there also. There's a formula, it's nasty, it's called Heron's formula. I actually could not remember that at 9 a.m. this morning. I couldn't remember the name of this formula, but I remember it now. So it's called Heron's formula. It's a disaster. We're not going to use it, all right? But there is a formula you can use. It's rather complicated, where if you have three sides of a triangle, and it doesn't even have to be equilateral, any triangle, then you can find the area using that formula. I'm going to use something else, though. I'm going to use this good old formula. So I need to, this is kind of a little bit of a review of pre-cal, and not even a review, it's just kind of like, you might have got through pre-cal without this, who knows. If somebody gives you a triangle, and it does not have to be a right triangle, if somebody gives you a triangle, if you know the height of this triangle, and you know the base of the triangle, which is this side, then I think we're all comfortable with this formula. Area is 1/2 base times height. Right? Seen that before? You're okay with that? All right. Anybody know where that formula comes from? Not really? I'll show it to you. It's pretty cool. Take this, okay, right-click copy, okay, so we make a copy of it. Now right-click paste, and throw another one down here. And I want you to turn it over. Rotate it like that. Okay? Yeah. You see that? That's a copy of this. All I did was just turned it like that. Okay? See it? So that's two of them, right? Now, you see where it's cut here? Take that piece, take it off the piece of paper and stick it right here instead. And now that's gone, right? And what do you have now? That's going to be a rectangle, right? This is height, and then this right here, well, this side right here is base still, here to here. So if I do base times height, that gives me the area of the whole thing, but this was actually two of them, wasn't it? So half that, and you get the formula. Okay, it's not important. So that's our formula. That's our classic formula for the area of a triangle. What's wrong with this formula? Why can't we use this right now? We don't know the height, do we? We don't know the height. The height would be this distance right here. Now, could we get it? Yes, we could. There would be some work. We could form a right triangle. We could just look at half of this. We could use Pythagorean's identity. We could do it, but it's too much algebra. There's another formula for area of a triangle that you should know. All right? Anybody know what it is? No? Just curious. All right. Here's the way it works. I'm going to add a couple of pieces to this triangle. I'm going to call this side A and this side C. Remember with triangles, we usually call them like A, B, C for the different sides? I'm going to call this angle right here theta. Now notice that is the angle between A and B. The area of this triangle is equal to 1/2 A times B times sine of theta. Does that at all look familiar? No? Yeah. Okay, so look at this formula. This formula usually freaks students out. They're like, where in the world did this come from? Because this looks kind of crazy, doesn't it? But I can show you how simple this formula is to derive. Take this right here in red. What type of triangle is this? Right triangle. Just tell me, in terms of all the letters we have there, what's sine of theta off that red triangle? Sine of theta is, it's opposite over hypotenuse, right? So h over a. Please solve that for h. Solve for h, and what do you get? A sine theta is h. Agree? Now come back over to this formula that everyone loves and replace h with a sine theta. And what do you get? You get this. You see? So this formula, the power of this formula is that you don't need to know the height. What you need to know, though, are two of the sides and the angle between them. And for our particular triangle, Do we know two of the sides? Well, we know all three, right? But we know two of them. Do we know the angle between them? 60 degrees. It's an equilateral triangle, right? So this is 60 degrees. So I can come up with the formula for that pretty easy using this formula. Got it? So I still need to come back up here and get that, but I'm continuing my thought over here. The area of this, pardon? Yeah, we're just going to tag the dx on the end. So really what I'm trying to find is the fill in the blank part right here. And so the area of this triangle is the fill in the blank part. The area should be 1/2 a times b, which is this side times this side. So 2 minus 2x squared squared, right? Then sine of 60 degrees. What's sine of 60 degrees? Sine of 60 degrees. 60 degrees, what's the y coordinate at 60 degrees? Root 3 over 2. Sine of 60? $60 degrees, what's the y coordinate there? Root 3 over 2. And so this I can rewrite as root 3 over 4, 2 minus 2x squared squared. I just brought the 3/2, root 3 over 2 up here to the half. And that's it, right? That's the area of that triangle. So when I come back over here and I want to know the volume of this little cutout that we made, I just needed to know the area of this times the thickness. I had the thickness, dx. The area is just that formula right there. So root 3 over 4, 2 minus 2x squared squared.
So for other triangles are not square, would it always be square root 3 over 4?
For other triangles, if it's an equilateral triangle, yes, it'll always be,
Other equilateral triangles
yes.
was my word. All we would change would be the middle complement, like the 2 minus 2x squared.
Yes, that's the part that's going to vary. The question was, you know, if we have another problem that's given to us and we're asked to find equilateral triangles, like what part of it's going to change? The only thing that's going to change is the subtraction of the two functions. You're always going to have the root 3 over 2 because you're always going to have 60 degrees on an equilateral triangle. And you'll always have the 1/2 because, well, the formula has a 1/2 in it. It's this piece right here that'll change.
Will there be a case where it's equilateral triangle?
I won't give you something other than equilateral triangle, but you could do like an isosceles triangle. Isosceles would be something like where two sides are the same, maybe like this, but that side's not. But if someone gave you that, they would have to tell you what the relationship between this side and these sides are. So maybe whatever this is, these sides are twice as long or something like that. You would have to be given that relationship. I won't do that to you. The book doesn't do it to you. I'm not going to do that to you. But even in that event, we could still use that formula because we know two sides and we could get the angle using properties of triangles and stuff. Okay. Fun stuff. Let's now get our final formula. What is the volume of the whole solid? Integral, right? Do we have any constants we can pull out? Root 3 over 4 can come out. And then we have the 2 minus 2x squared, that quantity squared dx. Forgot my negative 1 to 1. Done. And that's it. That's that last little topic. So the homework assignment that I put on the board last time, there was problem 38 and 39. Those two you really theoretically couldn't do. So now with this, you should be able to go